Hello class. In this video, we will be solving this problem. A 200 Newton sign is suspended by two cables making 30-degree angles with the ceiling. Find the tension in each cable. So let's list down the given quantities in this problem. So we're given that the sign has a weight of 200 newtons, or in other words, the Earth is exerting a gravitational force on the sign, which is 200 newtons. So it is specified in this problem that the sign is suspended by two cables. So what does this mean? It means that the ceiling denoted by the straight line, is exerting a tension force on the sign, which counteracts the weight or the gravitational force that the Earth exerts on the sign. So let's recall what a tension force is. So a tension force refers to a force that's exerted by an object on another object, and this is usually done through a material such as a rope or a cord. So you can think of the tension force as a pulling force that requires a object such as a rope. In this case, the ceiling is exerting a tension force on the sign through these two cables right here. And those two cables make an angle with the ceiling of 30 degrees. So we're required to find tension 1 or tension 2, tension 1 being the tension force that the ceiling exerts on the sign through this cable. Tension 2 is the tension force exerted by the ceiling on the sign through this cable. So we have this table right here, which lists down the x component and the y component of the force. So we're going to examine the forces that are being applied on this sign right here. So let's start with the tension force. So the tension force T1 that the ceiling exerts on the sign through this cable is given by T1. So let's examine the x and y components of this force. We can see through this green dashed arrow vector that we have T1y. T1y represents the y component of T1. For the x component, we have T1x, and that is the x component of T1. So take a look at these two vectors. If you notice, T1y starts from this point of the sign, ends at the ceiling, and from this point on, we have T1x, where we draw the tail of T1x, and end this point right here. So notice that T1y and T1x are treated as vectors, and the vector addition of T1y and T1x is simply the resultant T1, or the tension force that the ceiling exerts on the sign through this cable. So this is simply a vector addition. So let's take a look at the direction. T1y is going up, T1x is going to the right. So these are the x and y components of the tension force T1. Now let's examine the tension force T2. Let's examine its x and y components. For its y component, given by this green dashed arrow, we have T1, T2y, which is the y component of T2, and T2x being the x component of T2. Notice the direction of T2y and T2x. This is also a vector addition in which the result is T2. So T2y is going up, then T2x is going to the left. So these are the x and y components of both T1 and T2. T1 and T2. Now, what is the other force that is being exerted on the sign? That is the weight, which the Earth exerts on the sign. So we have the weight. Now let's list down those forces. So in the first column, let's list down the forces that act in the x-axis. So the x component of the net force. So we have T1x and T2x. Notice the sign of T1x is plus or positive, and for T2x, it's negative. And why is that the case? Taking a look at this, we see that T1x has a direction, or the vector that describes T1x has a direction that goes to the right. Meanwhile, for t2x, it's being described by a vector that is going in the direction and going towards the left direction. So this is why t1x is positive and t2x is negative. So always remember that the right direction is positive, left direction is negative. So these are the only components of the net force. These are the only components of the net force that act on the x-axis. Now let's move on to the second column for the y component of the net force. So we have T1y and we have T2y. So these are the y components of both the tension force T1 and T2. So notice that their sign is positive because T1y is going up, T2y is going up. Remember, the up direction pertains to the positive y-axis. This is why this is positive. And the other force, of course, is the weight. So that's given by negative W. It's negative because the direction of the weight vector is going down. So we denote that as negative. So these are all the forces that act on the sign. Now, notice that we have lots of variables, right? We have T1x, T2x, T1y, T2y. However, we need to find T1 and T2. So we have too many variables. So what we're going to do next is we're going to represent T1x, T2x, T1y, and T2y in terms of the original tension force vectors, tension force variables, T1 and T2. We'll represent them in another way. Now let's start with T1x. So notice that the vectors T1y, T1x, and T1, they form a right triangle, right? T1y is perpendicular to the ceiling, so we have a right angle here, which makes this a right triangle. Now, the goal is or what we're going to do next, as I've mentioned before, is we're going to express these four components in terms of the original tension force vectors. So let's use trigonometry in order to do that. So since we have a right triangle, we can express the sides of this triangle in terms of a trigonometric ratio. So let me write. So we have SOHCAHTOA. So if our reference angle is this, which is 30 degrees, which is the angle that this cable makes with the ceiling. So let's make that our reference angle. Let's try to find a trigonometric function that gives us T1y and T1. So given that our angle is 30 degrees, let's find that trigonometric ratio. Given, we can see that T1y is opposite to 30 degrees, and then T1 is our hypotenuse. So we're going to use sine. So if we take sine theta, then it's simply equal to the opposite side over the hypotenuse. So the opposite side is T1y, and the hypotenuse is T1. So if we multiply both sides by T1, multiplying both sides by T1, we find that T1y is simply equal to T1 sine theta. So the T1 cancels out. Then we multiply T1 here. Then I just I just switched sides. So the T1y, I placed it on the left side, and the T1 sine theta, I put it on this side. So we find that T1y is equal to T1 sine theta. We expressed T1y in terms of T1 and the angle that the cable makes with the ceiling, which is 30 degrees. So we have this. So here we go. Oops. So we have this. T1y is equal to T1 sine theta. Now let's do the same thing for T1x. We need to find the trigonometric ratio that gives us T1x and T1. So what trigonometric ratio is that? So that is our cosine. So cosine of theta still 30 degrees. So the adjacent is equal to its adjacent side over the hypotenuse. So the adjacent side of 30 degrees is T1x. So, and then the hypotenuse is, again, that is T1. So cosine theta is simply equal to T1x over T1. So doing the same process as before, or similarly to sine theta, if we multiply both sides by T1, then we find that T1x is simply equal to T1 cosine theta. So we have this equation that allows us to represent T1x, or the x component of T1, in terms of T1 itself. So we have this. T1x is equal to T1 cosine theta. We express T1y, T1x in terms of just one variable and the angle, which is theta. So let's do the same thing for T2y and T2x. Okay, so we will express T2y and T2x in terms of T2, or the tension force that the ceiling exerts on the sign through this cable right here. So notice that this, the vectors T2, T2y, and T2x, they form a right triangle together since T2y is perpendicular to the ceiling. So this is a right triangle. If our reference angle is still 30 degrees, or the angle that this cable makes with the ceiling, then we can use trigonometry in order to uh, represent or write a ratio between T2x, T2y, and T2. So let's do that. So again, our reference angle is 30 degrees. So let's start with T2y. So if we take sine theta, or the sine of this angle right here, 30 degrees in this case, then if this is our theta, similar to this right triangle, then sine theta is equal to T2y over T2, because this is the opposite of that angle right here, and T2 is the hypotenuse. So if we multiply both sides by T2 in this equation right here, we multiply T2, this cancels out, which leads to T2y being equal to T2 sine theta. So that's why we have this. T2y can be represented in terms of T2 by this equation. Let's do the same thing for T2x. So in order to represent in order to find the ratio that includes T2x and T2, we will use the cosine function. So the cosine theta, or the cosine of this angle right here, is given by T2x over T2, which is again equal to the adjacent side over the hypotenuse. So we find that T2x is simply equal to T2 cosine theta. So again, we did that by multiplying both sides by T2. This cancels out, which leads to this side, which leads to T2 cosine theta and T2x. So these two equations allow us to write T2x and T2y in terms of just the variable T2, along with the trigonometric function sine and cosine for T2y and T2x respectively. That's why we have this here. So now we express the four components T1x, T2x, T1y, T2y in terms of T1 and T2. Now let's find the net external forces that net external forces that are being applied on the sign in the x-axis. So looking at our table, for the first column, we have the x component given by the following forces, which is the x components of the tension forces T1 and T2. So remember, we so remember we represented t1x and t2x in terms of t1 cosine theta and t2 cosine theta. So we still have two variables, t1 and t2. That's why we will make an assumption. So let's assume that the cables are identical. So if we assume that the cables are identical, this would mean that the ceiling exerts the same tensional force along this cable and along this cable on the sign, because the tension force is dependent on not just the force that is being pulled, but also with the material. So if the cables are identical, then we can assume that the tension forces T1 and T2 are equal. If they're equal, then let's just use one variable to represent them both. Let's denote that as simply T. So with this assumption that the cables are identical, this allows us to equate the tension force T1 and the tension force T2 into just one variable. So we've applied this here in our net force equation. So the sum of all the forces that act on the sign of the x-axis given by T1x plus negative T2x can be simplified with just Tx minus Tx, since T1 and T2 are equal. Another way to look at it is with this. So remember, T1x is T1 cosine theta, right? Our T2x is negative T2 cosine theta. However, because of our assumption, we can write this as T cosine theta minus T cosine theta, which gives us 0. So that's one way to look at it. So the sum of all the forces that act on the sign along the x-axis is simply equal to 0. So this means that the sign isn't accelerating in the x-axis. It's at equilibrium in the x-axis, according to Newton's first law of motion. Okay? Now, because the sign is suspended, the problem doesn't say that it's moving, right? And because the net force on the x-axis is 0, this should also mean that the net force in the net external force applied to the sign in the y-axis should also be 0. Uh, because again, recall Newton's first law of motion, that in order for if an object is in equilibrium, an object is in equilibrium if the net force applied on the object is 0. So because the sign is suspended, it's not accelerating. It doesn't say that it's accelerating. We find that Fx is simply 0. Then Fy should also be 0, since the net external force is equal to the square of Fx squared plus Fy squared. Okay, but because Fx is 0, this should mean that Fy squared is 0 in order for the net force to be 0. So let's write that down. So the summation, or the sum of all the forces that act on the sign in the y-axis should be equal to 0. And looking at the second column of our table, these are the forces that are involved. We have T1y, T2y, and the weight. So the sum of all the forces that act on the sign in the y-axis is equal to T1y plus T2y minus W. And then again, by Newton's first law of motion, because Fx is 0, and Fy should also be 0. Now let's express T1y and T2y uh, in terms of T1 and T2. So for T1y, this is T1 sine theta. For T2y, this is T2 sine theta. And we have negative W. And again, this is equal to 0. So if we add W to both sides, we get the next line. So W equals T1 sine theta plus T2 sine theta. So W is equal to T sine theta plus T sine theta. So why did this happen? Again, because of our assumption that the cables are identical, T1 and T2 should be equal to T. So we can express T1 in terms of T, T2 in terms of T, uh, which is what we get in this next line of the equation. So W is equal to 2t sine theta. So this one and this one are the same. So we can combine them into 2t sine theta. Now, remember, the required is to find T1 and T2. But since we assume that the cables are identical, T1 and T2 are equal to T, so we're simply going to find T. So in order to do that, we are going to divide both sides by 2 sine theta, or in this case, let's plug in the quantities. So W is given by 200 newtons. Theta is simply the angle that these two cables make with the ceiling, 30 degrees. So let's divide both sides by 2 sine 30 degrees in order to isolate T. And we also divide 2 sine 30 degrees to the other side. So what is the result? So the 2 cancels out, the sine 30 degrees cancels out on this side, which leaves us with the tension being equal to 200 over 2 sine 30 degrees. So if you input this in the calculator, this should give you 200 newtons. So this is the tension in each cable. It is 200 newtons. So in order to check if our answer is correct, we can simply plug in this value, T 200 newtons, or basically T1 is 200 newtons, T2 is 200 newtons. So if our answer is correct, then if we plug in those values, this should be 0 and this should be 0. So I leave that to you as an exercise if you want to see that this is correct. But that's how you check if your answer is correct. You simply plug in the value back to our net force equations here. And if they match, then most likely your answer is correct. So this is how example S1, hanging sign with two cables, is solved.